With the recent technological advancement, robotics has proven to be an essential part from the fourth industrial revolution and has immersed itself in all aspects of our life. Hi, my name is Mahmoud Ali, and this presentation is on my final year project on joint space trajectory planning for the Fetch robot under the supervision of Dr. Pamela Carino Madreno. Fetch Robot is a common robotics platform that is widely used for research purposes in the robotics lab. The motion planning for the Fetch robot is carried out by using the Open Motion Planning Library Default Planner, which is called Rapidly Exploring Random Tree, or RRT planning algorithm. RRT gives a non-convex solution, meaning the solution found or the generated trajectory might be different even though no changes has happened in the environment nor the task. The objective of this project is to implement alternative planning algorithms. The results generated from the experiments will then be used to design evaluation matrices for these implemented algorithms, which then will be compared to the default planner RRT. This project also gives roboticists and research students the opportunity to work with more planners. Most of the research was done in Part A of this project to explore the planning algorithm alternative that can be implemented in the Fetch robot. And it was decided to implement the following two algorithms. The first one is Covariant Hamiltonian Optimization for Motion Planning, or CHOMP, which is a planning optimization algorithm that is able to generate a trajectory in multi-dimensional space using a functional gradient technique known as the gradient descent. It operates more efficiently in environments with no obstacle. One of the limitations of the gradient descent is that it causes CHOMP planner to be stuck in a local minima if obstacles were added to the environment. The second planner is known as STOMP, short for Stochastic Trajectory Optimization for Motion Planning. Unlike CHOMP, it does not require gradient descent, which solves the problem of stacking in a local minima. Instead, STOMP uses a cost function to satisfy object avoidance and motion smoothness. This project is mainly based on software, and the software used are Robot Operating System, also known as ROS, ARVIS, which is a ROS visualization tool, MoveIt framework for motion planning, and the simulation was done by the Gazebo simulator. Now, let's take a brief look at the functionality of this software in this project. Robot Operating System, or ROS, is an open source software. It uses topics and nodes to communicate the three parts of any robots, which are the actuator, sensor, and the controller. ROS Visualizer, or RVIS, is a powerful ROS tool that helps us to visualize the planning scene as well as makes the debugging process much easier. The following diagram is a high-level representation of the whole system that shows how all software used are communicating. Using ARVIS, 6 different tasks were designed to carry out the testing for the 3 planners RRT, CHOMP, and STOMP. The complexity of the task increases when we add obstacles into the planning scene. As you can see on the screen, in Scene 1, the planning for this task is simply done in an obstacle-free environment. The difficulty is then increased by adding boxes to the workspace as shown in Scene 2, which is considered easier than Scene 3, where the object is located very close from the robot manipulator. It is important to remind you at this point that we have only changed the environment or the planning scene, and all 6 tasks are still the same. Here we can see the full setup for the planning scene. The video shows ARVIS tool on the right of the screen is connected to the simulation of the Fetch robot in Gazebo on the left. We can see that the user is carrying out some motion planning, which is then being executed on Gazebo. At the bottom of the screen, we can also see the planned trajectories for the specified joints. Let's take a step back, because we cannot plan for these tasks without using planning algorithms. Hence, CHOMP and STOMP were implemented in the MoveIt framework to plan for these design scenarios. For CHOMP, the required pipeline file was set up for the planner to operate on MoveIt. However, for STOMP, the planner needed to, or the package of the planner was installed from GitHub, and the required files adjusted so that it can work with the movie group, and all the required dependency were also uninstalled. After we explain the methodology or the taken approach, we move to the experimental results. The conducted results are used to create or structure the evaluation matrix that have the following categories. First is the planning time. Second, success rate. And the last one is the trajectory quality, which can be split into two characteristics: smoothness, and that can be visually observed from the plots, and the second one is convexity. As I mentioned earlier, RRT planner is a non-convex because it generates different trajectory for the same task. Let's start with the trajectory quality. By carrying out a number of attempts of the same task using each of the three planning algorithms, as it shows in the graphs, CHOMP is consistent in generating the same trajectory in all three trials. On the other hand, RRT and STOMP give a different solution in each attempt. When it comes to smoothness, we can easily observe the plots, which shows that CHOMP is the one that generates the smoothest trajectory, followed by RRT, and the last one is STOMP. Next is the planning time and the success rate, which we were taking in the three different scenarios. The bar chart illustrates the planning time for each of the planning algorithm tested in the obstacle-free environment, completing 20 attempts for both task 1 and task 2. With no obstacles, CHOMP planner has the least time taken to plan for all 20 attempts for task 1 and task 2, while RRT has the longest time to complete or to compute the trajectory for both tasks. Also, all planners completed task 1 and task 2 with a 100% success rate. Next, we added some obstacles to the planning scene. As we can see in task 3, there is a significant difference in the planning time for RRT and the other two planning algorithm, CHOMP and STOMP, with CHOMP still having the least planning time. However, the success rate for CHOMP dropped to 40% in task 4, while STOMP and RRT maintained a 100% success rate for both tasks. In the last scenario, which is the most difficult compared to the first two, CHOMP has failed in all 20 attempts to find any solution, scoring a 0% success rate, while the success rate for STOMP dropped by 40% in task 5 and 15% in task 6. Taking less planning time than RRT in all attempts. This project opens the door to a potential advancement in the motion planning for the Fetch robot, which will start by first implementing CHOMP and STOMP into the physical Fetch robot. We can also implement a learning from demonstration algorithms to collect data and train the robot to complete more complex tasks. In addition, we can explore more trajectory planning algorithms that can potentially give a more optimum trajectories or solutions. I would like to thank my supervisor, Pamela, for all the guidance and support through this project. Also, I want to thank my family and friends for all their support. Thank you for watching.